Hello, in today's session, we're going to talk about the one-dimensional steady-state conduction heat transfer. So as you remember from the previous topics, we derived the governing equation for the three-dimensional case in the following form. The governing equation for conduction heat transfer, second derivative of temperature with respect to x plus second derivative of temperature with respect to y plus del 2t del z2 plus q dot over k, which represent the heat generation term inside the volume, equal to 1 over alpha, which is thermal diffusivity, del T over del tau or del lowercase t, which is time. They're the same. So this is the overall governing equation for heat transfer. For today's application or today's discussion, we are focusing on one-dimensional, which means that let's keep one dimension, drop the other two dimensions. Let's go ahead, drop the y and z dimensions, and let's keep the x direction. So we have del 2t del x2, and as you can see, it's a 1D steady state. And whenever we have a steady state condition, the time dependent term becomes 0. So boundary conditions are constant. They don't change with time. Since we don't talk about do we have a heat generation or not, let's keep this. If we don't, we set it to 0, but overall we would like to keep that. So if we simplify the governing equation where it's 1D and steady state, our equation looks like this. So for one dimensional, or we can show it as 1D and steady state, our governing equations becomes second derivative of t with respect to x plus q dot over k equal to 0. This is our governing equation. That's the governing equation we need to solve in this section, in this chapter, where we talked about 1D steady state. And just a quick reminder, Q dot represent the volumetric heat generation. The unit of Q dot was watt per meter cubed. K is our thermal conductivity. Watt per meter Kelvin is the unit for K. And of course, X is the dimension, T, capital T is the temperature. Before solving this equation, let's go ahead and talk about boundary conditions, as we will need to use boundary conditions later when we solving this governing equation. So let's have that discussion done before we go ahead and try to solve that 1D steady state governing equation. So let's talk about boundary conditions. I'm sure we discussed in previous sessions that boundary conditions are the information we can receive either experimentally or by observation or through any other methods from the boundaries of the problem, from the inlet, from the outlet, from walls, that gives us enough information to solve the problem. So one of the boundary conditions we typically see in heat transfer problems is whenever we have a constant surface temperature. So sometimes we can put a thermocouple on a wall, and we see a steady, constant temperature by time. So imagine temperature of the wall inside the room, which is air conditioned, remains constant over 8 hours, over 10 hours. That's a good assumption for a constant surface temperature. That's a good example for constant surface temperature. So how we show this case? In mathematical format, we are saying that temperature at a certain location, let's say at x equals 0, but at any time is constant. Let's show it with Ts at the surface temperature. Imagine this is my surface, this is my wall, or surface, doesn't matter. So let's show this surface as this. Let's assume the surface temperature that we monitored over time, which remains constant, call it Ts. And of course, air temperature beside it could vary. But if that's my starting point, if this wall is located at x equals 0 at this location, so we are saying that temperature at x equal to 0, so this is x equal to 0, or we show it as 0, and at what time? At any time is constant, which is equal to T sub s. That's our first boundary condition, and that's a very common boundary condition we see in many cases. Another case is when we have a constant heat flux. So number 2, constant surface heat flux. Well, we can have several cases. Let's divide this constant surface heat flux boundary condition into 2 general boundary conditions. First one, let's call it A, to be finite heat flux. If a constant known heat flux is kind of imposed on a wall, let's assume this is a wall, and we can show that there's a constant heat flux on the wall. We show the heat flux as Q double prime, and since it's on the surface, let's show a subscript S, so that represents the heat flux on the surface. Again, let's call that x equals 0 at the location of the surface, and x is in this direction. So in this way, we can say the heat flux is constant coming to the wall, and we can kind of use the Fouriers Law for conduction, if you remember, which is minus K variation of temperature, along the x at x equals 0 is constant, and that's equal to the heat flux. So if you kind of use the Fourier's law, you can reach to this equation. Well, one example of constant heat flux is that let's assume there's a lamp that converts electrical energy into light and heat, right? So let's assume the kind of efficiency of the lamp is known. At the constant efficiency, it converts a portion of constant electrical load comes in to heat, right? In that regard, if my power, electrical power to the lamp is constant, and let's assume efficiency of this lamp is, I don't know, 70%. So which means that 30% of that electrical energy is wasted, perhaps in the form of heat. So 30% of this maximum electrical power, P sub E, is converted to heat, which if the power coming to the lamp remains constant, that means that the heat getting out is constant. So that's a good example of constant heat flux, right? Or another example would be there's a solar radiation. Let's assume in a period of 9 to 9:10 a.m. in a particular location, when you measure that heat flux coming to the surface of the Earth can be assumed roughly constant, right? So in that case, you have a constant heat flux, and the amount of heat flux is finite, known, constant. So this is what we use for Fourier's law, for boundary condition from Fourier's law. Let me show you more details. What do we mean by Fourier's law and this boundary condition? Remember, Q with the unit of watt in Fourier's law is nothing but minus K A del T over del X, or dt over dx, correct? That's the Fourier's law. So everyone should know this, Fourier's law. When we want to get a heat flux has the unit of watt per meter squared, which means that we have to divide our Q with A to get the heat flux. So we get rid of the A here, so we have minus K del T over del X, right? That's the heat flux, that is amount of heat crossing a certain area. And by the way, the unit of heat flux is watt per meter squared. So in that case, all I have is minus K del T over del X is exactly what I have here. At this particular location at the surface is constant, and that's equal to heat flux at the surface. So that's kind of easy to follow using the Fourier's law. Part B of this boundary condition part B, where we have adiabatic another name for adiabatic is insulated surface. So what happens if a surface is insulated? Imagine I have a surface and I put enough insulation on the other side of the surface, and insulation makes sure that heat is not crossing the surface, right? So we're blocking the heat transfer because we insulated the surface. Another term is adiabatic condition. That means that the heat flux going through the wall is zero because of it's ideally fully insulated, right? So in this case, as we shown, minus K del T over del X at X equals 0. And by the way, this is my X equals 0, same as before, and this is the direction of the X. What happened to the heat flux? Heat flux becomes, in the previous example, we had a finite heat flux. It was equal to Q dot prime S. But in the case that is insulated, ideally heat cannot go through. That should be equal to 0. Again, another term for this would be adiabatic boundary condition. Again, you can use the same Fourier's law to derive this boundary condition, that at this location, Q double prime S going through the wall is 0 because it's adiabatic. One last boundary condition before we get into rest of the topic is convection surface condition. So that's where convection surface condition. That's when we have a convection on the wall. So let's assume we have a surface like this. And again, this is my x equals 0 location. X is start this way. And on one side of the wall, we have a fluid movement. So let's show it like this. And any fluid movement with convection, we show it with its temperature T sub infinity and with its heat transfer coefficient, right? So that fluid has its own H and its own temperature T sub infinity. So in this case, we can simply say the amount of heat coming to the wall by conduction. By the way, let me show my wall more clearly. This is my wall. This is my wall, which is a solid wall. Again, the only mode of heat transfer I have inside is conduction, which I modeled through Fouriers Law, right? So to show this heat going through my wall by conduction, by the way, this is my wall or solid material. I use the Fouriers Law, minus K del T over del X at x equals 0 right here. Whatever heat goes through the wall at x equals 0 at this location should be equal to the amount of heat we are receiving from the fluid. And remember from the previous discussion, first chapter, convection heat transfer or Newton's law of cooling represent or calculate, quantify the amount of heat going through by convection, right? So I use H delta T to quantify the amount of heat by convection. And what delta T? Temperature of the fluid, which is T infinity minus temperature of the surface, which in this case I can show it as temperature of the surface at x equals 0 and at any time, T, 0 and T. Lowercase t represents time. Let me show my 0 one more time. So this is what we have in terms of convection surface boundary condition. And let me discuss this a little bit more. Again, left-hand side is nothing but Fourier's law. Fourier's law. And what was Fourier's law? Q was, or Q flux, or heat flux, Q del prime was minus K del T over del X, right? For the case of Q would be minus Ka del T over del X, which with heat flux, we divide both sides by area. And Newton's law of cooling well, if you remember, was HA delta T. So in the case of heat flux, dividing by area both sides, you have H delta T, which is fluid temperature or T infinity minus surface temperature, right? So what we are saying here is that whatever heat going through from the fluid to the wall should be equal to the amount of heat getting into the wall, which we quantified that by Newton's law of cooling, and we showed this by Fourier's law. So this way, we have this boundary condition as we shown here. Well, now with the knowledge of boundary conditions, let's go back and try to solve the governing equation, which we have it here for 1D steady state conduction, the one in the box. So let's go ahead and solve it. We already talked about 3 different ways of boundary conditions we might see in our heat transfer problem. Now let's go ahead and solve it for the case of a plane wall. So Well, in this case, what we're going to do is let's consider a plane wall like this. Again, I'm showing my wall as this. Let's assume on two sides of the wall, we have two various temperatures. On the left-hand side, I have surface temperature 1. And on the other side, right-hand side, I have surface temperature 0.2, right? Let's assume this is my x equal to 0 location for the left-hand side wall, and the thickness of the wall is L. L can be any number. So the thickness of the wall is L. So the other side of the wall is located at x equal L. And by the way, this is the direction of x, right? Also notice here that I'm showing TS1 higher above TS2, which means that TS1 we're assuming to be warmer than surface temperature of 2. Okay, this is kind of what we do in that regard. Let's go ahead, solve the 1D steady state conduction heat transfer inside the wall, and ultimate goal is to find temperature distribution inside the wall. We would like to know what is the temperature at any x, any location inside you pick. We would like to know the temperature and how to do this. So remember, the heat equation we simplified for 1D steady state was d over dx k dt over dx. And of course, if you remember, it has the heat generation term equal to 0. In this problem, the plane wall, we are not including the heat generation, so no heat generation. So simply we drop this term. So all we will have is d over dx k dt over dx equal to 0. That's the equation we're going to solve for the plane wall. And of course, we will consider the with heat generation one as well later. So we know that for a constant k, if k is constant, then k multiply any function of x equal to 0. That means that if k is a constant, of course non-zero, that function should be equal to 0, right? So in this case, all we need to solve is d over dx dt over dx equal to 0. Because k times a function equals 0, that means that that function itself is equal to 0, okay? So we're going to solve this. As you notice how we need to solve this, we have two derivatives, d over dx of another d over dt. So we need to have two integrals to solve this problem, to get rid of the two derivatives. And of course, we end up with a few unknowns that then we plan to use boundary conditions to find those unknowns, and at the end to find the temperature T that we are seeing here as a function of x. So we know what's the temperature inside the plane wall at any location. Again, I need to do two integrals. So to solve this, double integral of d over dx dt over dx equal to 0. So simply you can say that, as you know, first integral, get rid of the first derivative. And of course, the integral of 0 is a constant. So we will have dt over dx equal a, and then we go one step further, take the second integral. Simply we say integral of dt over dx is equal to integral of a, right? You take second integral to both sides, and integral of dt over dx is simply t as a function of x, and integral of a constant is ax plus b, right? So this is what we get when we do double integral to our 1D steady state no heat generation equation. So this is the temperature distribution, but as you know, as you can see, A and B are constant. We would like to know exactly what are A and B's in terms of our problems specifics. So how we solve for A and B, we need to use the boundary condition, correct? So let's say to find A and B, let's use boundary conditions. So let's see what we do to find A and B. For using boundary conditions, or to understanding the boundary condition, we should go back to the problem itself. So we have two walls, one at x equals 0, another at x equals L. Let's see how we do this. For x equals 0 wall, we know that temperature of the wall at x equals 0 and at any time, of course, it's a steady state, so really we don't need to worry about time. And really all I can show is 0, but if I'm gonna kind of follow my note, let's do it this way, which again, a steady state doesn't matter what t at any time is equal to Ts1, right? Let me show it one more time. So temperature at x equals 0 is Ts1. So how we can use this? We have the governing equation, we have the temperature distribution equation. We found it by two integral we did on our equation. Let's substitute here to get what we have. So instead of x, I'm gonna use 0. I'm gonna replace x with 0, and of course for t, I have Ts1, right? So simply set x equal 0 and t equal to, and actually t at 0 equal to Ts1, right? So we will get Ts1 instead of Tx equal to A times x, and by the way, x is 0, plus B. This simply says A times 0 is 0, Ts1 equal to B. So one unknown is found. Great. So B is equal to Ts1. Now I'm going to use the second boundary condition that at x equal L, temperature at x equal L and at any time is equal to Ts2, which again, you can go back to your problem. You know that at x equal L, temperature of this wall is Ts2 is given. It could be 40 degrees C. It could be any number, right? Or in general, we call it Ts2. And let's go ahead, use those L and Ts2 into our generic solution of temperature. What we get is temperature is equal to A times X, which in this case, my X is L, plus B. And what is B? I'm going to use Ts1 for B because I just found it in the previous step. Correct? That should be equal to Ts2. By the way, this is B. Right? So I'm looking for A. A is simply TS2 minus TS1 divided by L. So this is my second unknown. I found A, I found B, and all I need to do is go back, replace it into my temperature equation, this equation. T is equal to AX plus B. I found A, I found B. So T was AX plus B. So temperature would be A times X. A, we found it to be this. Excuse me, which is TS2 minus TS1 divided by L. That's my A times X plus B, and B was equal to TS1. So, and this is my final answer for the plane wall case, right? So this is showing me the equation I have to find temperature at any X, at any location. If I know the boundary conditions, TS1 and TS2, and I know the thickness of the wall, I can use this to find any temperature. As you notice, this is a linear line. So the temperature is simply a straight line going from TS1 to TS2. And as you notice, at any location, at any X you would like, you can go ahead and find that temperature by that equation. So I hope that's a straightforward. Let me repeat the XL one more time in case I did it pretty fast. So for the case of X equal L, temperature at L is equal to TS2. How we know this? By given boundary conditions. So the problem should give this information to you. At X equal L, temperature is called TS2. You're going to substitute those values in this generic equation. So A times X, in this case L, plus B, in this case my B is TS1. I found it from previous step. It should be equal to TS2. That's the boundary condition. And from here, just isolate A, everything else on the other side. This is what you get. So this is the solution we have for plane wall. Let me show you how we can use it in one simple case before moving up to composite walls. So this is the equation we have. That's my final answer. Let's go talk about the Fourier's law quickly. Remember, Fourier's law is used to model conduction, heat transfer, right, inside the walls. And I'm sure all of you remember Fourier's law. Q is minus K A dt over dx, right? For a 1D, we show it with D. For multi-dimensions or 2D or 3D, we show it with del or partial derivative. But hey, in this case, it's 1D dt over dx. Now, let's go ahead, take the derivative of temperature with respect to x. And by the way, we have our temperature equation just derived, so let's use that. So if I use this temperature and take the derivative of this with respect to x, dt over dx would be, so dt over dx of this term is 0 because TS1 is constant, and the second term is a coefficient multiplied by x. So really derivative of temperature with respect to x of this term would be just TS2 minus TS1 divided by L, correct? So that becomes the derivative of the temperature equation we have in this red box. So if I use that, I can show that. Let's use the same color. I can show that Q is equal to minus K A. Instead of dt over dx, I'm going to use TS2 minus TS1 divided by L. Okay, or in order to not show negative sign, we can also say Q is K A TS1 minus TS2 divided by L. Kind of substitute the locations or change the location of these two. So this is another way to form the Fourier's law inside the plane wall. If you know the temperature of both lines, so if this is my wall, and the thickness of the wall is L, 10 centimeter, 15 centimeter, and can be any number. Temperature of this side, let's call it TS1. Temperature of the other wall is TS2. And to quantify the amount of heat going from high temperature to low temperature, that's the direction. All I need is thermal conductivity of the wall, area that heat is crossing, times TS1 minus TS2 divided by the thickness of the wall. This is another way to show the Fourier's law inside the plane wall. With that, we're going to finish this session. Next session, we're going to talk about composite walls in Cartesian and cylindrical and spherical coordinate systems. Thank you so much. We'll talk soon.